Okay, so finished chapter 20 in this organic chemistry. We are going to look at some more reactions of carboxylic acids, then maybe go through some practice problems from the various chapters. Try to get you guys ready, because once we get through chapter 20, I'm going to give you a test over chapters 18, 19, and 20. Reactions of aldehydes and ketones, reactions of amines, and reactions of carboxylic acids. So let's start by finishing off chapter 20. We left off talking about ways to reduce carboxylic acids. We talked about, like, well, if I add a lithium aluminum hydride, I can go from a carboxylic acid to a primary alcohol. The mechanism isn't fully understood. We know that we produce some sort of hydrogen gas, and we use water as the source of some of the protons. That there was an alternative scheme that we use borane and THF, which is very selective to reduce the acids versus the ketones and aldehydes. Because remember, lithium aluminum hydride will reduce any reducible position. So borane served as a way to reduce the acids first. Most of these reductants will knock them all the way to primary alcohols, however, so we need a way. What if we want to stop halfway? We don't want to have to reduce it all the way to a primary alcohol and then oxidize it again. Anytime we can cut 2 steps down to 1 step, you're going to increase the yield and make your life a whole lot easier. So we're going to, in order to reduce the aldehydes, we still will have to go through an intermediate, but this intermediate is very high yield and very, very reactive. So we're going to form an acid chloride, and we're going to talk more about these guys next chapter, but we have a functional group R C double bond O O H. There's our functional group. Now we're going to react with thionyl chloride. So essentially SOCl2. The structure is essentially oxidizable position of thionyl dichloride. Now what this is going to do is going to kick off our alcohol, going to fully oxidize that sulfur and deposit the chloride onto there. And then from there, that is much more reactive, such that we can use a reductant that is very selective and it's like this is not going to reduce as many positions. Right? Lithium aluminum hydride tert butoxide. Now there's only one hydrogen one hydride it can transfer. So it's only going to transfer it to this thing. And you notice the tert butoxide, those are going to be lots of steric bulk. It's going to keep this from keep on adding. So what the byproduct is going to be our aldehyde. Let me do this. So we're going to see this more in a minute. We're going to look at the mechanism of how do we form this acid chloride. But so this acid, we're going to essentially form a very reactive acid chloride, and then use a weak reductant, a sterically hindered reductant to fully oxidize. to produce that only partially. Sorry. Okay. Another thing we can do, we can calculate our ketones. We've seen this. We've seen this. Well, we have, oh, I have a carboxylic acid. We did this a bit in a way to make ketones. So you can add 2 equivalents of our alkyl lithium and then water. 2 equivalents of alkyl lithium and then water. Now we did that. The alternative was to add base lithium hydroxide first. That could have, before you add the alkyl lithium. But it could be done either 2 equivalents of the alkyl lithium or a base in alkyl lithium. So what is going on? Let's remind you what is going on. Alkyl lithium as well as Grignard are good nucleophiles, but they're also very good bases. Remember, what is a carboxylic acid? An acid. So what will acid do to a base? Well, the first step is we have our R minus 5 plus. The base will attack the acid and generate R carboxylate. That carboxylate, we can associate that with lithium. So carboxylate salt. But that lithium then, that carboxylate can then be attacked by the other equivalent of our functional group, kicking that up. So moving that down, we have R carbon O minus R. Well, that's not really very stable. Not really very stable at all. A dioxylate, not very stable, but that's what our water is there for. Our water is there for to protonate these guys. In the presence of water, we can protonate these guys to form a diol, a geminal diol. OH, OH, and here's where we get a little bit of rearrangement. We talked about this too, that hydrated ketone can form this diol on back. So eventually this lone pair goes up to attack that. Bond goes down to swing here, and then we have our ketone. This may be our more stable form, generating water as the byproduct. So this is something we discussed before. We're just discussing it again as a quick reminder that, hey, there is a lot of ways that we can make these, but it's all building on what we know. We're going to see the same kind of reactions over and over and over again. The only thing to really remind yourself is that, oh, some of these reactants are less reactive. So we can synthesize and use acid chlorides. We just kind of talked about acid chlorides a few seconds ago. But so, thing to note as acid chloride is they are very reactive, very, very reactive. You've got the carbonyl, which is already very polar. but then usually have this inductive effect of the chloride, which is pulling electron density away. But unlike the usual hydroxy group, this is also a very good leaving group. A very good leaving group. So we're often going to make these guys. Now, there, as I said, there's two. Well, I already told you one way we can make these guys from the carboxylic acid using the SO2, SOCl, diCl, but we can also do it another way. The other way uses oxyl chloride. So this is called COCl2. Oxalyl chloride. The structure is actually a diketone, well, diacid chloride. So we have a ketone, we have a carbonyl functional group next to a chloride, next to a carbonyl functional group next to a chloride. These guys are, this guy, one of the big things is that these guys will form gaseous byproducts, which is why it's going to push this to products, or this is going to push us to products that essentially that this guy is going to form what? The SOCl2 is going to form SO2 and HCl, which you can boil off easily, which is why you get very, very high yields. Now this guy, not going to form SO2, but it's going to form CO2 and HCl. So once again, gaseous byproducts that you can easily boil off and remove, thus forcing this guy to products. It's not going to be a reversible reaction. There's not really any side reactions. So we can essentially form acid chloride. The two major reactants are SOCl2 or COCl2. But how does this work? So let's look at this. So the first thing, we're going to use SO2 because that's one of the easier ones. But it's going to have a very similar mechanism. Remember, when we think of mechanisms, the lone pairs, the base always attacks the acid. I know we want to have the positive attacking the negative, but we always have the negative or the lone pair attacking the positive. The electrons are doing the movement, not the absence. So S with 1, 2, 3, 4, technically 5, 6. But we have a lone pair. It's going to attack here, kicking this up. We form this intermediate R C O O H. This guy plus Cl. And this can resonate with this structure, R O H plus. So we have these two structures resonating back and forth. Well, Well, the first thing's going to happen is the lone pair on this oxygen is going to swing back down to get this the ketone and kick off. It doesn't really matter if it's going from here or there, but it actually probably favored this version. So either way, we're kicking off chlorine as a leaving group. So with that chlorine as a leaving group, we have this structure. Still not super stable, but we're within reason. And there's a Cl minus. Well, see where that happened. This is not super stable. So what is going to happen? You're going to first extract a proton, forming HCl gas. So what do we got in here? It's going to shift over to form RC double bond O, O, S double bond O, Cl. HCl gas can now leave, forcing that from reverse, keeping that from reversing. Now, I know this is kind of jumping the gun, but we have, so say we have some chloride left over. Not all the HCl necessarily leaves, but from there, we can have our nucleophile chloride coming and attacking functional group and kicking that up. But we're going to regenerate this chloride in the end. So O minus, O, Cl. That up, and of course, once again, swinging back down, and then moving that off. What is it? Moving that here. Causing that to leave. So we could swing that and kick that chloride back off and get back to there, but this reversible step would be back and forth, back and forth, back and forth. It's when we kick that guy off, we form our product, we lose our SO2 gas, and then, well, crap. This leaves. This definitely leaves, whether the HCl left or not. We regenerate our chloride, which then can be used and further on keep the reaction going. But this SO2, when it kicks it off, that is a definitely irreversible step. Maybe this is a reversible step. Maybe it's a reversible step to get to there, but this, when we lose that SO2 for sure, we're going fully irreversible at that point. So why are these guys good? Why is it important why go through this? Well, you can use this for a lot of different things, a lot of different reactions that were very reversible before, and we had to force them to products. We had to find some way to, you can use these for ester formation without having to worry about the reversible step. You go, oh, I'm going to use this, and I mix this with some sort of alcohol, and you're going to have an intermediate of R, C, O, O minus, O plus, R prime, where this is going to swing back the lone pair is going to swing back down, kick this guy off, and we'll form, oh, there's our let's see, O, R prime, H plus, and that's going to be deprotonated by the chloride. But this is going to be a much more stable product than this. This guy is much more stable, and thus this guy is going to be more favored as you mix them together. You're not going to have to use an excess of alcohol or some heat or some way to force this away from the acid and to the ester form. This is going to be pretty much irreversible. Now, typically, it's going to form HCl as F. HCl is the byproduct. Now, typically, what you can do to take care of the HCl is use pyridine, a base, nitrogen base, to neutralize the acid. That's going to further force this to products. As you remove that proton, pyridine is not exactly a strong base, so it's not going to exactly deprotonate an alcohol, but it will be protonated in the presence of a strong acid. So alcohol, not going to react with the pyridine. HCl will react with the pyridine. So you can force this, you're forcing this to products. You're using the Chateliers. So I'm removing HCl, so I'm going to keep moving forward, making a better acid that's going to lose its protons, which is going to protonate pyridine. You can form amides the same way. RCOCl. You mix in some sort of amine in the presence of, say, sodium hydroxide or pyridine again. Pyridine. And you have our and you don't have to worry about reversibility. You form, oh, if I did sodium chloride NaCl in water, or if I did pyridine, it would be like sodium pyridinium. So that is the last reaction of this chapter. And so right now, let's look at some problems. Let's start with chapter 20 and move backwards a bit. So I had assigned some problems in the book. Chapter 20, I said 25 A, B, and E, 35 A, B, D, F, G, H, I, 40, and 45. So I'm going to go ahead and look at, say, the ones on 35 I looked at. Say, like, determine the products of these reactants. So we have, let's say, cyclopentane. So cyclopentyl methanoic acid. That might be the easiest way to name that. And they say, oh, we're using lithium aluminum hydride. And water. So, reductant, only one reducing spot, and it's a strong reductant, so it's just going to literally kick this all the way back to the alcohol. So CH2OH. So cyclopentyl methanol. So the B, we have a say, I'd say a 1-cyclohexenol, it's like, let's see, methyl bromo, 1-cyclohexenol, or that's a hard-worded name, but so we have the first step is sodium cyanide. Second step is acid and heat. So what the first step does is it is an SN2 reaction that's going to kick off my bromine, replace it with cyanide. Now the second step, the acid and heat, is going to exchange the nitrogen for water and fully oxidizes. So what this is going to effectively do is add effectively what we've done is replace our bromine with a carboxylic acid and ammonium byproduct, which can be removed. Now D we have what, like 2, 3, 4. That's 4-octine, where we have the triple bond in the middle, and they say, well, let's use permanganate, hot and concentrated. Permanganate, hot and concentrated, is a really strong reductant. It will fully oxidize this and cleave that bond in half. Now, and leaving all CHs remaining. Well, because there's no CHs there, it's going to fully oxidize it. Now, because it split it directly in half, you have 2 equivalents of our butanoic acid, being that it's going to split, if it splits that in half, you have the same on both sides. That's D. Let's see. We'll keep going. F, G, H, and I. F is a phenyl, 2-phenyl butanoic acid, and we react with borane and water, or borane and acid. So that's just going to fully oxidize that. I'm going to leave that CH2 and OH. It's just a alternative oxidant. Now this one is interesting. This one is Fischer esterification. And they tell you it ends up with a cyclic ether. So what's happening is we're going to lose a water and cyclize this. So this is essentially going to connect to there. So we have 1, 2, 3, 4, and the oxygen makes 5. So it's a 5-membered ring. And water is the byproduct. But Fischer esterification, that is actually going to be faster than a molecule-to-molecule reaction. Intramolecular bonds are often faster than intermolecular reactions. Now this one's not too bad if you remember this. So we have aromatic ring filled by 2 non-aromatic rings, and they say, oh, let's use permanganate, hot concentrated. Well, this cleaves off every bond, not quite there. Let's see if I can undo that without, cleaves off every bond but the first associated with that phenyl ring. The phenyl ring is untouched, so the phenyl ring stays the same, but it's going to oxidize everything else. So it's going to keep oxidizing, but it cannot oxidize that phenyl ring. So it's going to leave that alone. So oxidize that. Every other carbon is going to be turned into CO2. This guy would like to be turned into CO2, but it cannot because we're not going to touch that ring. That just forms a dicarboxylic acid. The last one, this is a good one. So we have a bromocyclohexyl ethyl, and then we have a protected acetal. Remember, acetal is just a fancy way of protecting a aldehyde or ketone. So essentially a very reactive group. Why would we want to protect the group? Well, we're making a Grignard. So first step is to make a Grignard. So that's going to put the magnesium right there between the bromine. Now, if I left that alone, that would immediately attack the aldehyde that we have right there, and the aldehyde that we have protected. And thus, you're going to have an intermolecular reaction between this and its identical molecule. Now, by adding CO2 and having that protected, we now Grignard attacks CO2 to form a carboxylic acid as a Gutterman conct. So we have but it needs to be protonated. It's going to be O minus. So we add acid, but acid is a way of deprotecting acetal. So not only do we form our carboxylic acid that we want up here, we deprotect our aldehyde down here. So that goes back into acetal from aldehyde from acetal. That is the byproduct. So yeah, I don't think about acetals and reactivity. I'm going to skip straight to 45. This one is an interesting problem. The story goes that essentially a teacher was wanting to give various aldehydes and ketones and have people test them by IR and NMR, and he put this heptanol in a tube for several days before letting the students test it. So heptanol. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. That's 8. Shoot. Okay. But the students all got this guy wrong. They all did not see the expected peaks of 1720, which is our C double bond O. They didn't see the 2710, which is our CH, our CHO peak. And they didn't see the 2810, which is our basic CH. They didn't see those peaks. Instead, they saw a broad 3000 peak, and they saw 1715 peak, which isn't too far off. So we still see some sort of carbonyl. And the note is this is also water soluble. That is a dead giveaway if you don't already know it. So the bottle tested, yeah, I have heptanol. So, but the test tube coming up with this. So what happened? Well, in this case, is the students right or the teacher right? Well, they're both right. The teacher put heptanol in the heptanal in the tube. He absolutely did. The bottle's still good. There's nothing wrong with the bottle. But the students did not have heptanol in the test tube. They had heptanoic acid. That broad peak at 3,000 is the OH stretch of heptanoic acid. And the fact that this is water soluble suggests that we've increased the polarity from the traditional carbonyl into something more polar like a carboxylic acid. So how could this have happened? Well, the fact that he left this uncovered in a test tube for several days, that aldehydes are very reactive. In fact, they can oxidize in air by themselves. It's a slow process, but the fact that he left it for several days, he's not like he made it fresh the same day, said, oh, he could potentially let it be oxidized. Oh, how could he solve this? Well, he could store this in an airtight container so as not to let that oxidize. So I thought that was a real interesting one based on real life. Okay, so jumping back to chapter 19, look at some reactions of amines. Reactions of amines. I assigned 32, a bunch of 32, which is naming, some 33, which is determining acidity, 38, which is some reactions, 39, which is some more reactions, and 59, which is a fun little one about drugs. Well, let's look at some reactions, at least to the end of class. So 39A, so they say specifically an excess of amine, of ammonia with phenyl bromide. That, remember, phenyl, one phenyl, or let's say 3 bromo, 1 phenyl propane. That ammonia is a nucleophile. It will attack and replace this and alkylate amine. Now, this will do it multiple times. So how do we prevent that from doing it multiple times? Either have, well, how do you prevent a mixture of products? You either have an excess of amine or you have an excess of bromide. You either make sure it fully goes to products or you keep it in one way, keep it in all either make sure it only adds once or make sure it adds as many times as possible. Okay. Now, reaction C is using a N-methyl, a nitrogen ring and hydrogen peroxide. Hydrogen peroxide is an oxidant. It's going to oxidize the nitrogen to the best of its ability, but it's not going to kick off any carbons. So the only thing we can add is 1 oxygen, so O minus. That's all it can do. There's not going to be any ring opening or anything like that. Without any further steps. But this idea can be done in part E. I didn't assign D, but I'm going to actually do D. No, I don't have the book with me. But I say problem D is actually an extension of that. So you do the next step. But like say problem E, that clear. E and F are directly related. E step 1, they add methyl iodide. Step 2, they add silver oxide. And then step 3, they add heat. Point here is to fully methylate this nitrogen, and then oxidize it so that it's going to, and then the heat causes this to ring open. Now it doesn't matter which side you draw it with this, it's going to ring open one side, and this is the Hoffman reaction. 1, 2, 3, 4. And it's going to create the least substituted product. Now F is essentially do this again, times 2. So we're doing the step 1, step 2, step 3 again. So what are you going to do? Well, what's the most substituted product? I could break that bond, or could break that bond. Well, that bond is going to make a di-substituted alkene. This bond is going to make a mono-substituted alkene. So we're always going to try to make the least substituted product. So the product here is going to be, for F, is dimethyl 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4. So essentially, you're going to have these two alkenes. Now we can maybe kick that off some way or another, but okay, no, that's not charged. Maybe kick that off one way or another, but we have essentially formed two Hoffman products on this. Remember the Hoffman, to do that, we're going to add a lot of methyl iodide. We're essentially add a lot of methyls, oxidize this, and then use heat to break it off. Now we can have lots of other reactions. We can have the Clemmensen reduction, which is we add the zinc to our nitrogen. It's going to fully oxidize this. It doesn't have to be zinc, but a lot of oxidizable metals in acid. I'm going to fully reduce this from nitrobenzene to aniline, which is a amino benzene. Then letter L, that was H, there's L. We have a benzene with a cyanobenzene with a phenyl group. Cyanide. And then the reaction is a lithium aluminum hydride. Once again, this is going to reduce something that is oxidizable. We have the CN. Well, CN is, we have a bunch of double bonds. We can add more hydrogens there. And so we're going to reduce that as far as it can go. And so water. So we're going to fully reduce that to amino. Now, if we added acid instead of lithium aluminum hydride, we could have exchanged that for a carboxylic acid. But because we added lithium aluminum hydride first, we're going to keep reducing that. Now looking at do 39, the 39 questions. I did 39 B, C, D, F, and G. We'll finish off after those. So 39B, we have a pyridine, fluoropyridine. So the fluorine is a leaving group that we can exchange in here. When we have a methoxy. This one's not really too fancy the reaction. But like some of these are just aromatic reactions. Some of these are. So C, we look at, well, we have a nitroaniline, which of these guys is more reactive. So the nitrogen, so this one we had HCl and nitro. NO2. This is going to, and then CuBr. NaNO2, remember, is going to form the diazonium with a amine. But it's only going to form on the amine. It's not going to react on the nitro group. So the diazonium will become a very good leaving group. And so we can exchange the amine for a bromine. Why might we want to do that? Well, nitro group, remember, is a deactivating group. It might not be too easy to add a bromine after that, the nitro, but we could add 2 nitros to this. Well, yeah, so it might not be so easy. We might be add amine, I don't know. But, so we can do that. Let's see. D, we have just a ketone, and we add first KCN and HCN. So hydrocyanic acid and cyanide, and then lithium aluminum hydride. Cyanide attacks there. We pronate the alcohol. So we have a cyanohydrin, but then the cyanohydrin at the second step then becomes oxidized. Well, it then becomes fully reduced. So step 1 forms this. So C triple bond in. But then step 2 is going to fully reduce this guy down to CH2 and H2. And there's 2 more. Step, this one is we go, okay, bromine. We're going to add, this is the forming a Hoffman product. So step 1 is I'm adding a trimethylamine to this guy. So this guy is still a better leaving group than the bromine. We're going to kick that off, and we're going to have and 1, 2, 3. And then the step 2, we have the silver and the heat. So what is that going to do? That's going to cleave this, and we're going to form a double bond, the least substituted spot. So we can either go there or there. Which one's fully substituted? Well, the left one. So it's just a convenient way of anti-Zaitsev. If you tried to do, say, the E2 reaction, you're going to get the Zaitsev product, which is going to be the secondary in the alkene, the internal alkene. Now, using this, a little bit harder, but it will form your external alkene, the terminal alkene. Last reaction. That's right. So we're doing a cyclohexanone. Then we're adding, in the presence of acid, we're adding an amine. So remember, alkenes, I mean, not alkenes, but ketones and amines are exchangeable depending on what you're adding. So you form an imine. And you lose water as a byproduct. So that's the last reaction for 39. So those are just a few handy reminder reactions that we've seen we have. So with that in mind, want more organic chemistry? Like, subscribe. For actual Bethel students, remember that careful, like online interactions may change. You careful what you share and who you share with. Have a good day and good luck on the test.